So now we want to set up the finite element formulation of a system by using the Galerkin method, which is one of the weighted residual approaches. Now I want to get straight to the example. So if you can think about the problem that we were already solving before, then we had the governing differential equation as A E du dx minus p is equal to 0. Right, so the formulation of the residual for this problem will start with setting up with substitution of u into the differential of this function. So we will consider the differential of the governing equation. So the differential d dx of the governing equation would be ae du dx minus p is equal to 0, is just going to be d dx of ea du dx, because p is a constant. So that's all will remain. So this is going to start as our this is going to be basically the function that we are going to start with, the differential of the governing equation, and therefore the when we write this in the form of d dx of ea du dx and we bring the 0 to this side, so there's nothing to remove, this becomes equal to the residual. So that is basically the function that we are looking for the as a residual. The weighting function always has to be equal to the number of unknown coefficients that we have, of course, and in this case the weighted residual always the weighting function always has to be the shape function as I had defined before. So therefore we can say that the shape functions n, which were given as ni, nj, are the weighting functions as well. Okay, so let's start first with the displacement function. So we have to have an assumption for the displacement function, and that we already know. We know that the displacement function for a certain element will be given as n times u. And if we are going to spell it out completely like we did before, then we can say xj minus x by L and x minus xi by L are ni and nj for the two nodes. Then I have ui and uj. So the weighting function is actually taken as n in this case, as I already explained before. So with the Galerkin method, I had an integral a of b, a to b, wi r dx is equal to 0, right? So here I have the residual to be equal to ae du dx, and then I have my weighting function w to be equal to ni n j, or I can also write it as n. So if I put it together in the Galerkin method integral, or the Galerkin integral, then I will get for a certain element that I've already discussed before in other videos. This is xi, this is xj in terms of x, and this is ui, uj. Then I can have an integral from xi to xj over the length of the element of the residual times the weighting function n. I'm not going to write it in brackets, I'll just write it like this, so you assume that you have to know this is a matrix or a vector depending on the size. This is equal to 0. Now if I want to put this correctly, then I can also, because I want to have consistency in terms of the matrix notation, then I can write n transpose in front, d dx ea du dx. Sorry, I keep switching between ae, but those are just constants, so it shouldn't be such a big problem. Now this is, if you look carefully, this is a classic integration by parts problem. Okay, so if you do the integration by parts here, I'm not going to spell it out for you because I expect you to know this. If you don't, you can find many sources. And in that case, I will have also another slide if you would like to later on published that shows you exactly how to do it, but I trust you can. So if I'm going to integrate it by parts, I will be left with n transpose ea du dx, which has to be filled in for xi to xj, minus integral of xi to xj e a du dx, because I can integrate this part already in the integration by parts, sorry about that, and differentiate the other part, which is n transpose dx is equal to 0. Now if you solve this particular problem for a single element, especially when we have already defined a certain example in the shape function video where xi is equal to 0 and xj is equal to L, then you can simplify this above equation quite easily. So I'm going to carry this equation forward to the next page, and I'm going to rewrite it here so that we don't miss it. So you have n transpose EA du dx over the limits xi xj minus integral of xi to xj EA du dx times dn transpose dx is equal to 0. Right? Now we already know UE is equal to NU, which can be written as, by the definition that we already know, xj minus x by L, x minus xi by L, ui uj. Okay, so we can find out du dx, because that's how we can put it back into the equation. So you have du dx is equal to xj is a constant, so I can write it as minus 1 by L, and this as 1 by L, ui uj. So that's the derivation for du dx, and it's the same if I want to do it for dn dx, which would be the same thing. So if I say n transpose is actually equal to ni nj in a column format, which can be written as the same xj minus x by L and x minus xi by L, and the dn transpose dx can be written as minus 1 by L and 1 by L here. So if I actually put it together for this, then I will have EA du dx, which is given as minus 1 by L, 1 by L, and dn transpose dx will be minus 1 by L, 1 by L, and there you will have ui and uj. And this can be simplified as EA by L square, 1 minus 1 minus 1, 1. So you can solve this. This is of course plus 1 by L to get this relation quite easily then. This is multiplied with ui uj. Now if you put this back into this highlighted equation here, then it has to be over dx, and dx of course from xi to xj is going to equal to L, so one of the L's here will be removed. So we will get, for this term alone, we will get a term which will be, let's call this term b. Then b here will be equal to EA by L, 1 minus 1 minus 1 1 times ui uj. If you look carefully, this is nothing but the stiffness matrix, 1 minus 1 minus 1 1 times the displacement vector u, that is given as the same relation as b. Now we can take the rest to the other side, or we can also just do it here. It's quite easy to figure out that this is nothing but the boundary condition. So if you look at the equilibrium equations again, then you know that EA du dx at x is equal to xi is equal to pi for a certain element in free body diagram. So this is pi and this is pj. So if you look at the complete equation, then you know, let me write it here again, EA du dx minus p is equal to 0. So we know that at xi or ui p is equal to pi, and xj or ujp at xjp is equal to pj. So those are basically just boundary conditions that can be put on the other side. So ultimately your equation will then I'm going to switch back to the black color, will look like K 1 minus 1 minus 1 1 times Ui Uj is equal to Pi Pj. And this is very, very similar to the relation that we have been working out so far for equilibrium in a finite element analysis.